Well, good morning, everyone. My name is Kevin Ortwiste. I'm the spring team lead for Team Cooch Street. Here we have Jake Nyland. He was the team lead in the fall, and also Rob Rodriguez and Alex Harlan. Over here, listed on the right, are these fine individuals. Without them, without their support and guidance, this project would not have been possible. So our academic advisor, Dr. Hoffbeck, and our industry rep, John Turner, who couldn't be here, and our client, Will Taylor, who also wasn't able to attend as well. So this is what we're going to go over. We're going to quickly tell you what frequency beats is, and then go into how it works and the implementation of getting this thing to do what we want it to do, and end on a great demonstration, at least we hope. So, frequency beats, what is it? In the end, frequency beats is an audio visualizer, so it represents the magnitude of the low, mid, and high frequencies in an audio signal. Most of you will be familiar with seeing this kind of on your computer, or like LEDs flashing up and down, that sort of thing. But what makes frequency beats unique is that it utilizes ferrofluid, which is a fluid that reacts to magnetic fields, hence the orange electromagnets on the top of the display, so you can see that. So here is the overall circuit schematic of the project. With this, I'm just going to give you a really quick brief overview on how this works, but then the other teammates will then go into the fine details. So as you can see, the audio enters from the left, first goes into the Arduino. The Arduino then processes it and measures the magnitude in each frequency range. There's going to be a low, mid, and high. It outputs it as a PWM signal, which is then sent to the control circuitry, which then in turn controls the electromagnets. So more detail on the actual control circuitry. Again, this is the control circuitry. There's 3 of them, one for each electromagnet. So as you can see, when there's a PWM signal seen coming from the Arduino, so that gets cleaned up by a low-pass filter, and we register it as pretty much a high, smooth DC source, DC signal. And as a result, the emitter is greater than the voltage at the base. The voltage at the emitter is greater than the voltage at the base. So the transistor then turns off, and thus the base of the MOSFET is pulled high, and that turns the electromagnet on. Whereas when you see this sort of PWM signal coming from the Arduino, that's registered as a low after the low-pass filter. Thus, the transistor is turned on, and the base of the MOSFET is pulled low, and the electromagnet turns off. In addition, you can see there's the switch, this 3-position switch. That there is used for debugging as well as just overall control of the electromagnets. In the middle is a no connect, so the electromagnet's always off regardless of what the Arduino is doing, and all the way to the, your right, the electromagnet is always on regardless of what the Arduino is setting. And so now, Alex is going to talk about the electromagnet and the construction and efforts we put into that.
So we'll go over a little bit of how we design the electromagnets and the displays you can see up here. So as far as the electromagnets, our initial design plan was to use 110 feet of 22 gauge magnet wire wrapped around a 1/2-inch diameter metal core. That would be 5 inches in length. This would have given us an internal resistance of about 1.77 ohms, and our goal was to hand wrap these magnets. What our final design wound up being was 270 feet of 26 gauge magnetic wire wrapped around a 1/4-inch diameter iron core, still 5 inches in length. This gave us a total internal resistance of approximately 13 ohms on each magnet. We wound up wrapping these using a lathe as opposed to hand wrapping them, and that kept the coils tighter and closer together, though it was a slower process. So some of the reasons for making these design changes, we needed to increase the length of the wire to get a strong enough field to actually move the ferrofluid. As far as the change of diameter, that was based solely on what we had available. We didn't have any 1/2-inch diameter rods, so we went with 1/4-inch. As far as using the lathe, that made the big difference. The lathe was a vastly slower process, but ultimately yielded a vastly superior magnet. So you can see up here the materials we used. In the center we have the 1/4-inch diameter iron core, cut in half to 5 inches, and then we fixed a plexiglass end cap on the end, which wound up being the top part of the display that you can see here. For the electromagnets, on the left is the one we hand wrapped, so you can see the coils aren't very tight or close together, whereas the one we wrapped with the lathe on the right is really tight, really close together, and looks like something you would get professionally manufactured. As far as the displays, our initial design plan was to use plexiglass. We had a long 2-inch diameter plexiglass thing we were going to cut and use that. We were going to fill it with homemade ferrofluid using toner and vegetable oil. Our final design wound up being a bit different. We used glass cylinders, 1 inch in diameter and 2.5 inches tall. We filled them with ferrofluid that we bought online. Next one. The reason for these specific changes, the homemade fluid that we made just wasn't that great. We couldn't get the consistency, and even if we could get a decent consistency, it still wasn't reactive enough. The plexiglass seemed to allow ferrofluid to stick to the sides and mucked up the display so you couldn't see anything, which wasn't what we wanted at all. Again, if you look here on the far left, you'll see the homemade ferrofluid in a test cylinder. It wasn't that great. In the center is the purchased ferrofluid and a plexiglass cylinder that we built. As you can see, you can't see anything, so that wasn't a very good option. And then on the right is our final design, which was the glass cylinder with the ferrofluid that we bought encased in water, which turned out to be really reactive, as you'll see during the demonstration. So here we have the 3 final displays that you can also see up front. And next, Robert will tell you a little bit about the software implementation and the Arduino that we utilized.
Okay. So going along the same lines of initial design and final that Alex went along, our initial plan was to use a fast Fourier transform algorithm that would quickly sample the audio signal and compare the amplitudes of each frequency in the audio signal within the Arduino do itself. However, we had a whole lot of problems with the IDE not being compatible, the IDE being updated and changed to a newer beta version still, and just general problems in the algorithm not cooperating well with the libraries available. So at about a month into the build stage, we had to come up with some plan that would allow Alex and Kevin to actually troubleshoot their magnets. So instead of using the Arduino to process, we swapped it out for a chip, 8-pin chip, MSG EQ7, which basically does the processing for us. It wasn't very clean or exact, but it gave us the 7 bands that we needed to produce frequency outputs needed for their testing. Eventually, though, we got ourselves to work the processing. Came out to be exactly the same as the initial design. Took weeks, even months to troubleshoot, but we got it to work. We adapted a customized library from online resources, how to implement the algorithm itself using other languages, and also basically just write our own library so that it was compatible with the IDE, because everything we were using was not. So, and to go a little more in detail for what's actually happening in the Arduino, we have an initialize function which basically sets up the variables and initializes the input and output pins so that the Arduino can take in signal and output the processing. And inside the loop itself, it continuously samples the analog input through the 3.5 regular standard audio jack, performs the FFT, and produces real and imaginary parts of the signal in each bin. We take the magnitude of each bin and combine them into the listed frequency ranges. 80 Hz to 255 is the low range, 255 to 6K is mid, and 6K to 12.5K is high. The audible range actually goes up to about 20K Hertz, but in music you don't generally get that high anyway. The average, after we get them separated into those bands, we average each one's amplitudes, magnitudes, and we get a single value for each of the 3 ranges. We output to a low-pass filter, which then normalizes the average magnitude value to give a smooth, even pulse width modulation signal, and we repeat that. And next we'll be giving it over to Jake, who will talk more about the FFT itself.
So I'm going to talk about what the FFT is actually doing. I'm not going to go into the math, mostly because that would be a class in and of itself. But you can see here the Fourier transforms signals between time and frequency domain. It's measuring the amplitude and frequency of, or in our case, an audio input. The graph you see on the left is an input of about 3 Hertz, and the output here you can see is I can't read these numbers, but this is a 2 and a 4, so you see a peak at 3 Hertz. This is exactly what we want from the Fourier transform. To explain kind of what's happening, we're taking samples of the voltage coming into the Arduino, and we're taking 512 samples at around 47,000 samples per second. And this is, the red you see is the samples we're taking, and the input signal is supposed to roughly represent those samples. Because the way the FFT works, it actually kind of folds in half in order to calculate faster, because we want this to be in real time to, pulse with the music. So we actually only have 256 workable samples. Each bin is approximately 85 hertz. There's a little bit of variation in there, but to give you an idea, bin 1 would be 85 to 170 hertz. And you'll actually see when we do a frequency sweep that bin 0 is a reference bin, so it gives a lot of noise, and the low frequencies will turn on even when it's not necessarily representative of a low frequency. And I want to explain the PWM. So the way the Arduino works is you have a function given to you called analog write. You get a value between 0 and 255, and that will output based on the duty cycle of the Arduino. So at 25%, a value of 63, you'd see it on 25% of the time, 127, 50%. It keeps going. At 255, though, it's a full on. So it would just be an output of 3.3 volts, just turning the magnet on directly, never off. And let's see it actually work.
Okay, so the first thing I'm going to show, just like I mentioned earlier, the three switches here. Right now they're in the middle, so even if we are playing music, nothing's going to happen. But if we move the switches over to the right, your left, you can see that force the magnets on. I'm now going to move them over to the other side so that when Robert plays something, that the magnets will also actually react to it. So first we're going to do a little frequency scale up sort of signal, and Jake's going to talk about that while that's playing.
Actually watch it kind of move across. You can see the noise here from that reference bin at 0. This one will start turning on in just a second. The way that we have it, there's a lot of overlap between these two frequencies. So we did it that way because the music looks best then, so when you're actually playing a song through the device, it just kind of looks better, and you'll see that in a second here. Let's watch on the watch.
Come on in, it's time to begin whether you're ready or not. So when the dance gets hot, don't look for reasons why not. Come on in, it's time to begin whether you're ready or not. So here I go. With a baseline low.
You can see it actually will represent how intense the volume is, and that's where we're getting the magnitudes, those peaks on the FFT. Turn it back up, you can see they're pretty much all on when it's on high volume. So now they're pretty much all on high volume.
So in closing, again, told you what frequency beats is and explained rather briefly how it works and what we had to do to get this far. Before we open up for questions, I would like to recognize Jared Rees. I didn't mention him at the beginning, but he was also a huge help. He gave us access to the lathe, Alex and I access to the lathe, so we could spend the 6 hours coiling the electromagnets, but he also really helped us with just this, helping us with the circuit and debugging and whatnot. So thank you again, Jared. Okay, so that's all we have. We're opening up for questions now. Any at all?
Perhaps I missed it, but you mentioned the reference has a noise level or something. Why is that one as opposed to the middle and the high?
That's the way the FFT is calculated, and in the particular algorithm that we're using, it's, if I could actually show the output of the calculations, you'll get really huge numbers being put in just as a reference, like this is your input signal, and then afterwards that algorithm will say, okay, now each of the frequencies in this range are at whatever magnitude it gives you. So basically it's, as far as I could tell, all of them combined in one bin in order to do the calculations.
Okay, thank you.
Any other questions?
Okay. Well, thank you for coming.